Now this is an important derivation. Poles on a conductor in a magnetic field. Current carrying conductor in a magnetic field. Okay. So look at this. We have a magnetic field that is going from left to right. Look at this. Magnetic field lines are drawn this way. Magnetic field lines are drawn similar to electric field lines, right? Electric lines start from where? Positive. They end on negative. Similar way, magnetic lines start from a north pole and they end on a south pole. So there must be a north pole sitting here and a south pole sitting over there. Got it? Okay. And then you're going to keep a conductor inside this. You're going to keep a conductor inside this. See the conductor? I have a conductor that is kept this way. The conductor is kept this way, like this. Okay, we have a conductor like a copper wire or something. Copper wire. Alright. The copper wire is making an angle of theta with the magnetic field. I repeat the context one more time. This is a current carrying conductor. Alright, I am passing a current through this. Okay. I am passing a current through this. So it is a current carrying conductor now. Alright. A conductor with a current passing through it. Where is it kept? It is kept inside a magnetic field. Alright. So what happens now? Actually, the current flow is what? Current flow is flow of electrons. Right. Who constitutes current flow? The flow of electrons. Am I correct? When I say current flow, what I mean is the electrons are flowing. Correct. So the electron, billions of electrons are in fact flowing inside. Billions of electrons. Okay. All those electrons are moving where? Inside a magnetic field, right? Inside a magnetic field, right? An electron moving inside a magnetic field will experience a force. What is the equation for force? Do you remember the equation for force? We wrote just now. QVB sine theta. Because a charged particle Q moving with a velocity V at an angle theta entering a magnetic field B will experience a force QVB sine theta. Right. I'll tell you the context one more time. This is a current carrying conductor like copper wire. Copper wire. Alright. Current carrying copper wire and it is placed inside a magnetic field. Inside a magnetic field. Okay. Then what? The current is flowing. Current is flowing means electrons are moving. Billions of electrons are moving. Those electrons are moving inside a magnetic field. Correct. So they will experience a force. Altogether, the conductor will experience a force. I'm going to find the force on the conductor. Force is given by QVB sine theta. Alright, QVB sine theta. Now, let us look at this. What is Q here? You know, I can say Q is equal to N into Q is equal to, I'll tell you an easy method here. You know, okay, fine, right. So this is what? Imagine the volume of the conductor. Area of the conductor is A. Area of cross section is A. Length of the conductor is L. Volume of the conductor will be A into L, right? Area of the conductor is A. Look at this. I have a circular cross section. This is the wire. Wire usually has circular cross section, unless mentioned otherwise. Okay. So this wire, area of the wire is A. Length of the wire is L. So the volume will be what? Volume will be volume of the conductor. Plus volume of the conductor is what? Volume is equal to area into length. Area into length. So what will be the number of electrons inside? Number of electrons will be ALN. Because I take N as number density of electrons. Number of electrons per unit volume. Number of electrons per unit volume. That is, if I consider a unit cube inside, unit cube means what? A cube having a length of 1 centimeter, breadth of 1 centimeter, height of 1 centimeter. It is called a unit cube. Okay. It has a volume of 1 centimeter cube. Got it? The number of electrons inside it is called number density. Number of electrons per unit volume. Got it? It is fixed for a given metal. Okay. For example, if I say N is equal to 10 raised to 28 per meter cube for copper, 10 raised to 28 per meter cube. What does it mean? In 1 meter cube of volume of copper, there will be 10 to the power 28 electrons. Got it? So it is called number density of electrons, which we have seen before. Number of electrons per unit volume. So one volume has n electrons, two volumes will have 2n, three volumes will have 3n, seven volumes will have 7n, Al volumes will have Aln, right? Correct. I got the number of electrons. I can find the charge now. What is the charge? Therefore, charge is given by the first equation we learned this year. Charge is equal to Ne, right? Ne. That is equal to N. I have gotten over here. ALNE. Finally, I'll put it back to this. F is equal to what? F is equal to what? That is QVB sine theta. And what is Q here? Q I got here. Tell me what? ALNEVB sine theta. Last step. You know, this thing you have learned before in current electricity. NEAV. That was called I. That was called ISCS. That was called I. Okay, right. It is I. This is called I. So that's going to be I. Circle is I. The rest of it is LB sine theta. So force is given by ILB sine theta. Or in short, you can call it F vector is equal to I into L cross B. The force acting on a conductor is given by IL cross B. The force, direction of force can be found out using Fleming's left-hand rule. Fleming's left-hand rule. Not right-hand rule, left-hand rule. Hold the first three fingers in three perpendicular directions. And then first finger represents field, FF. Central finger represents current, CC. Then thumb represents thrust. Thrust means the direction of force. I did not use F because F is already taken for force field. Okay. First finger, but never use this for numericals. Use the vector treatment. That is always better. I will show you how to do it. Okay. I repeat one more time. This is about force on a current carrying conductor. We have a current carrying conductor placed inside a magnetic field. Okay. What's happening? Electrons are continuously flowing inside. Those electrons move inside a magnetic field. Correct. At what angle? At an angle theta. So they must be experiencing magnetic force. What is the equation for magnetic force? QVB sine theta. And in this equation, I'm going to find out Q and substitute. All right, charge. How to find the charge? Volume of the conductor is A into L, area into length. Area into length will give you the volume of the conductor. If I know the volume, I can find the number of electrons inside. Number of electrons inside. How do I find it? Volume into number density. Number density means number of electrons per unit volume. Number of electrons per unit volume. In one volume, there are n electrons. Two volumes, 2n. Al volume, Aln. I got the number of electrons, right? I can find the charge now. How to find the charge? Charge is given by Q is equal to Ne. The very first equation we learned in class 12. Q is equal to Ne, quantization of charge. So you get charge as N is equal to, I got number of electrons from here, Aln into E. Okay, I put into this, Aln into VB sine theta. But the circle terms, you see this, NEAV was called I. So that makes it ILB sine theta. Force on a conductor is given by ILB sine theta, which is I into L cross B. All right, L cross B. And the direction is given by Fleming's left-hand rule. FF, first finger represents field. CC, central finger represents current. Thumb represents thrust, the direction of force. Okay. And there is a numerical which I did in class. You know, that is very important. Textbook numerical. You know, imagine you have a conductor here and then you are letting a current pass through it. Now tell me what? This is a current carrying conductor, right? Correct. Now it is trying to fall down. This is trying to fall down because of its weight. If you know, weight. What is my condition? I want to keep it stationary in space. Because that's a very important question. This is it's a textbook reader question. We have a conductor that's kept this way. And as I am trying to drop it, it's falling down. But I want it to stay stationary. How can I make it happen? Give another force. Which chapter is this? Magnetic effects. So I must be thinking about magnetic force. In electrostatics, we had a similar one, Millikan soil drop experiment. There we used electrostatic force. Correct. Here, in order to balance gravity, I'm going to use magnetic force. How do I give that magnetic force? That is given by ILB. Just apply a magnetic field like this. Now this is what? A current carrying conductor inside a magnetic field will experience a force ILB. Weight is mg. If they balance each other, what is the condition? Mg is equal to ILB. In the reader, the question is to find out magnetic field required. Or I don't remember exactly. But anyway, let us take B. What is this? Mg divided by IL. And they have taken this together, these two together as M by L has a name. It is called linear mass density, mass per length. Mass per length into G divided by I. Nothing. They will give you mass per length in the question. I did this before your exam. Okay, mass per length in the question. Acceleration due to gravity, you know, it is 9.8. Current, you know, you can put them out. You can put them here and then find the answer to this. All right. Now the previous board question is this. I did this in class before exams. There will be like 3 conductors, 3 or 4 conductors this week. And there is a magnetic field in this direction. They will be asking you to find, it's a repeated board question. They will be asking you to find the magnetic field force on each conductor. For this conductor, length is 8 centimeters, if I remember correctly. And the current was 10 amperes. It's a board paper question. ILB sine theta. Theta is what? 0. Because conductor is on x-axis. Magnetic field is on x-axis. Parallel, right? Theta 0. For this conductor, the height was 10 centimeters. So their angle is 90 degree, right? 90 degree. Got it. ILB sine 90. For this one, this angle was given, say 30 degree, but we are supposed to use this angle. Why? We need the angle between the conductor and the magnetic field. Right. What is theta here? The angle between the conductor and the magnetic field. Correct. So this is the conductor, this is the magnetic field, and this angle is 60. Okay, this is given to put you in a trap. Okay, that angle is not needed. All right. This is 90 degree. If this is 30 degree, 90 plus 30, 120. You know that this angle is 60, right? Altogether it is 180 now. So ILB sine 60. Got it. And the last one is a straight conductor. Again, this is on x-axis. Field is on x-axis. They are parallel, right? Correct. The conductor is on x-axis. The magnetic field is also on x-axis. They are parallel. Theta will be 0. Got it? ILB sine 0. Force will be 0. I will show you something now. Look at this. Now this is what I wanted to show you. This is the force acting on a conductor. Right. See this. See this? That's a current carrying wire. Right in the middle, you can see a giant magnet. Do you see the magnet here? Right. This black one is a magnet. You are passing a current through it. When you switch it on, current passes. It becomes a current carrying conductor. Right? It will experience a force. Okay. And later on, he will reverse the direction of current. What will see what happens to the conductor force? Force also reverses. See, when the current is switched on, the conductor experiences the force, right? It's going up this time. But when you reverse the current, see what happens? It's going down. This time the force is down. You didn't understand? Yeah. First part, even the force was up because the current was going one way, and second case, the current was going the other way. So the force is just opposite. It's the same thing. It should be the same thing. Same thing. The conductor experience emerges. Okay. Anyway, later on, tomorrow we will see a torque on a coil. And in fact, I taught this, but I will be teaching that again. Torque on a coil in a magnetic field. See this? This is also, in case I am not able to show tomorrow. You have a coil here. That's a magnetic. That's a coil wound over a core. Coil, copper coil. Okay, and he is going to bring a pair of magnets close to it. See what happens. It's a current carrying coil. It automatically starts spinning, right? You see that? Okay, so it's already a current carrying coil. When you bring it close to it, automatically it starts spinning because current carrying coil inside a magnetic field will experience a torque. Will experience a torque. Okay, understood this, all of you? All of you understood?